So let's look at this example then. dm dx equals minus w L minus x, where w and x are constants. I take issue with that, where w and x are constants. X is our independent variable. So what we're actually after is how m varies in terms of x, which they say later anyway, so I think, you know, x is not a constant. I don't think in this situation. So x is our independent variable, as is stated here effectively. So we're going to end up with a plot of x, distance along the beam, against moment, for the moment of the beam. So this one's quite straightforward, because all we've got to do with this differential equation is to integrate both sides. If I take the dx over the other side, I've already got all the x's on the right hand side, so dm equals minus w L minus x dx, where x is our independent variable. So then I'm just going to integrate both sides. So I'm going to integrate the left hand side with respect to m and the right hand side with respect to x. So just to be clear, looking at the left hand side, integrate dm actually is as though there's a 1 there, so I'm integrate 1 with respect to m, it just brings the variable back again. So what's the integral of 1 dm m? So that's going to give us our explicit form straight off. So the integral of the left hand side is just m. And let's play around with the right hand side to try and make it a bit more integrable, is if that's a word. So what I'm going to do is multiply out the brackets, minus w times L, minus w times minus x is plus wx dx. So just got to be a bit careful with signs there. So then I'll be tempted to write the wx first, minus the wl. I always write the positives first if I can in these things. I mean, there's always more than one way to do these things. I suppose in some ways I might have been tempted to take this minus w outside the integral, because it's a constant. And now when we get to here, w is with both of them, so I could take that w outside the integral. But it doesn't matter, you know, at this stage. We're always going to get to the same answer. It's just that how you go about doing it and what you see. Well, what I'm going to do now is effectively integrate each one separately, remembering that x is the independent variable. So that's going to involve adding 1 to the power dividing by the new power. But this bit, it's just like a constant, a number, wl. So that means if I integrate it, the variable just reappears. So if I pause, you could just write down what you think the integral is going to be. So hopefully for the first term, add 1 to the power divided by the new power for x. So I get wx squared over 2. And for the second term, wl is just a constant, so the x just reappears. wlx plus c. So there's our general solution. This bit. If you've got your general solution, by the way, and you want to check it's right, if I differentiate this, I should get back to this, shouldn't I? Back to that. And if I differentiate this, I get this term, I get 2wx over 2, which is wx, that's this. If I differentiate wlx with respect to x, the x disappears and I'm left with that. And if I differentiate a constant, it's gone. So we get back to what we started off with if we differentiate it. So if you're unsure that you've done your integration correctly, differentiate it and you should get back to what you started off with. Okay? This is our general solution, because we don't know C. But can we go further? Can we come up with a particular solution let's look back to the original problem. It tells us that when x equals 0, m equals this, a half WL squared. So I can put those conditions back in. So I can now say that when x equals 0, m equals a half WL squared. So I can put them into this general solution. M equals a half WL squared equals, when x is 0, so the first two terms are gone, see, so it automatically gives us what c is, because the other two terms in there will both be 0 if x is 0. So now I can write my particular solution. M equals wx squared over 2 minus WLX plus a half WL squared. So this is the particular solution. I just want to tidy it up a bit, so I'll leave a bit of room for myself here underneath. Again, algebraically, it might be worth trying to play around with this. I've got a half in this one over 2 and a half in this one, so I'd quite like to take that outside the bracket. This is not a half, so if I times it by 2 over 2, then I actually do have a half. So I can also, and also w is in all three, so what I'm going to do is actually say that m equals w over 2, and then I can write down what I'm left with inside the bracket. So what am I left with inside the bracket? What are the three terms that I'm left with inside the bracket? Just see if you can do that, and I'll pause it here while you do it, and then we'll write it down. Hopefully you get w over 2. What do I times that by to get back to w over 2x squared? X squared. Next one, bring the w out, but I've got to times by 2 and then Lx. And if I multiply w over 2 by minus 2Lx, I get back to that middle term. And then last one, if I take the w over 2 outside, I'm just left with L squared. So hopefully you got that, which you might want to write your how you might want to write your particular solution, tidied up a bit. It actually turns out to be x minus L all squared if I do that. If you multiply out x minus L squared, you get x squared minus 2Lx plus L squared, which is this. And actually writing it like that, or even like this, you can ask yourself the question, what happens if x equals L? If x equals L, this becomes x squared. So I get 2x squared here, and that's x squared plus another x squared is 2x squared, so actually we end up with 0. And you can see it even more clearly if you write it like this. If x equals L, then the moment is 0 effectively, which is quite a nice way of looking at it. Now if we look at a model, what's happening here? If I plot it, I get this for our particular solution. This is the model. And it's telling us what's happening to the bending moment on a beam as we move away from the end. Now I think actually when I was right the first time on yours, I think it's this way round. Let's just talk about it for a minute and we'll see. The bending moment is around here, around the beam, isn't it? Because it's not suspended at one end, it's only suspended, it's fixed there, and so it's sort of a hanging beam. So what's going to happen to the moment? No, it's 0 at the end, isn't it? And then it goes to a maximum here, is that right? I think it is. If it's fixed at that end, we get this bending moment that turns that way. So the bending moment is 0 here at this end, and then goes to a maximum bending moment at this end. So I think I should have drawn this. If you're going to plot it for the correctly for the graph here, if I fix it that end and have it free at that end, that looks like it. And so now we're measuring x as this distance here. As x increases, no, x is measured from the free end. X is measured from the free end. Because when x equals L, then it's 0. That's right. Which is what we want. In other words, this describes now exactly what the moment is going to be on the beam at any point. What's the moment on the beam at this point? What's the moment on the beam at this point? What's the moment on the beam at this point? What's the moment at the end? 0. What's the moment at the fixed end? 0.5 for this particular example. But we can now predict, because we've got the function, what the moment will be at any point along the beam. It's described by this formula. And probably the most useful way to write it would be like that. But this is the particular solution here. So all three are the same, just written differently. So there's a lot of algebra in these things. Differential equations, solving the differential equations is only the half of it really. It's what we do with the solutions at the end to model a situation.